We are told that we have a random variable x which has an expectation equal to mu x and a variance equal to sigma squared x. We randomly sample n independent and identically distributed observations of x. So we've got x1, x2, x3, all the way up to xn. Now all of these are themselves random variables. Every time you take a different sample from the population, you get a different realization of x1, a different realization of x2, and so on. So these vary depending on the sample that we observe. We're going to use the sample mean, which remember is equal to 1 over n times by the sum of the xi's, as an estimator for the population average or the expectation. So the sample mean here is our estimator of mu. Now we've said that the xi are themselves random variables, and we know that because the observations are randomly sampled from the population, and they are, more importantly, they are independent and identically distributed, then it follows that the expectation of each of those xi's is equal to mu x. The variance of each of those xi's is equal to sigma squared x, and the covariance between xi and xj, because the observations are independent, that is going to be equal to 0 for I not being equal to j. Now we need to try and find the variance of the sample mean, and that will give us a measure of the variability of the sample mean across samples. So to calculate the variance of the sample mean, we're just going to apply the variance to x bar, which is equivalent to finding the variance of 1 over n times by the sum from I is equal to 1 to n of xi. Now we already know some rules about what happens when we take the variance of some combination of random variables. We know, for instance, that the variance of any constant times by a random variable is equal to a squared times by the variance of the original random variable. Now in this case, 1 over n is a constant multiplier of the sum of the xi's. 1 over n is not a random variable. It doesn't vary across samples. It just is a fixed value, so we can take that outside of the variance, and we can rewrite this as being equal to 1 over n squared times by the variance of the sum of the xi's. We also know that the variance of any sum of random variables is equal to, if it's the variance of y plus z, it would be the variance of y plus the variance of z plus 2 lots of any covariance terms. Now we can represent that in this case as being equal to the variance of x1 plus x2 plus x3 plus all the way up to xn, and we've got the variance of the sum of n random variables. So we can apply this rule that we've seen over here, and we can represent this variance of a sum as the sum of all of the variance terms plus 2 lots of all of the covariance terms. So we can write this as 1 over n squared times by the variance of x1 plus the variance of x2 plus the variance of x3 plus all the way up to the variance of xn And then we're going to have two lots of all of the covariance terms. So we'll have the covariance between x1 and x2, the covariance between x1 and x3, and so on, all the way until we get to the covariance between xn minus 1 and xn. Of course, this notation that we've used here is quite expansive, and we can simplify this using summation notation. So we can rewrite this as being equal to 1 over n squared times by, first of all, we've got the sum of all of the variance terms. So we can represent that as the sum from I is equal to 1 to n of the variance of xi. Then we're going to represent all of the covariance terms. So we've got two lots of the sum from j is equal to 1 to n minus 1 of the sum from k is equal to j plus 1 to n of the covariances between xj and xk. And what this is representing is all of the possible pairs of covariance terms. So that will include the covariance between x1 and x2, the covariance between x1 and x3, the covariance between x2 and x3, and so on. So this includes all of the possible pairs of covariances. But because the observations are independent and identically distributed, it follows that the covariance between the observations is equal to 0. This is particularly because the observations are independent from each other. So that must mean that all of these covariance terms are going to be equal to 0. Because the observations are independent from each other, the covariance terms will be equal to 0. Similarly, we know that as the observations are independent and identically distributed, the variance of each of those random variables, the variance of each of the observations, is going to be equal to sigma squared x. So we can rewrite this whole thing as being equal to 1 over n all squared, but that's the same as 1 over n squared, times by the sum from I is equal to 1 to n of sigma squared x. But this term is just sigma squared plus sigma squared plus sigma squared n times, so again we can rewrite this as being equal to 1 over n squared times by n lots of sigma squared x. We can tidy this up a little bit. We've got an n on the top and an n squared on the bottom, so one of those n's will cancel, giving us that the variance of the sample mean, if the observations are independent and identically distributed and randomly drawn from the population, is going to be equal to sigma squared x over n. If the observations weren't independent, then the covariance would be non-zero, and the variance, the formula for that variance, would be much more complicated.